but I'll give it a shot and see how it works out. I'm already not a fan because I have to stand on this side of the room where all you guys are over there. So there's kind of a disconnect. So a couple of things that I wanted to actually discuss had more to do with some of the mathy side of things. So, my view is statistics and probability basically comes in two different forms. Statistics is more the practice part of it, okay? For me, it's a little, definitely there's advanced statistics stuff that you can do moving forward, but most of what you learn in this lecture will be a little bit straightforward. When it comes to statistics, probability gets a little bit more challenging, okay? And I want to provide some of that challenge to you guys, at least on the mathematical side. And it will, let's just say, it might not develop you for tomorrow, but maybe further down the road, okay? Start thinking more mathematically, especially if grad school is in your mind, okay? So one of the first things, and I know this, might be a little bit pedantic to some, but I think it's worth going through, is some of the notation that's commonly used, okay? Even though all our assignments are on WebAssign, I don't want you guys to lose fact of the importance of the notation, okay? Because everything means something, and especially in grad school, you're going to want to be using the right vocabulary, right? Just like we speak to each other in a common vernacular that everybody understands, and we try not to speak pidgin English, mathematics is the same way, right? We want to be clear about when we're talking about specific things. And so there's a few notational items that sort of got brought up. Just from the beginning, we can talk about, when we start talking about samples of a variable, sort of the common notation that we see in the book is we talk about x1, x2, x3, ... to some, oops, and there goes my dead spot, xn, okay? And so what that means is we've basically taken n samples. Right? If I'm going to refer to an arbitrary sample, then I just refer to it as x of I, all right? Or so there's some arbitrary ith sample. So that's fine and dandy. How do we use that? Okay, well, we see it sort of get used right away when we start calculating means, right? So what's the symbol for a sampled mean? X bar, that's right. All right, X bar. All right, so actually let's do this. So sample population. Okay, so if we're talking about the average, all right, we write X bar. All right, if we're talking about the population mean, what symbol do we use? No. All right, what about for the, let's do this, mean. Median. Does anybody remember what the symbol is? The squiggly? Yeah, the tilde on top. All right. And conversely, we have the squiggly on top of the mu. Okay. What other symbols did we learn in this chapter? I think there was one other. Yeah. All right. So standard deviation. So which is which? So say again? S for the sample, yeah. Okay. And sigma for the population. Okay, and of course we can do variance as just the square of that guy. Okay. All right, so this, I mean, okay, learn it, get it in your head. Understand when you see one or the other what people are talking about. Okay, so typically in probability, we'll be using these guys. And in statistics, or actually I should be careful, what are the two types of statistics we have? All right. Okay, so typically if we're doing, actually I have to be careful even saying that. So the only time we'll pretty much use these is in statistics. Sometimes in statistics we'll actually be using these guys as well. Okay, so if we have our whole population, okay, so if, what were they doing again? Descriptive. All right, so if we have our whole population and we're doing descriptive statistics, then we're actually talking about our population, right? If we're doing inferential statistics, then what we're trying to do is estimate these terms in our population, okay? But we'll be able to estimate this right column using our calculations in the left column, okay? And that actually gets touched upon very, very briefly, but in this chapter, and I think we'll see it more in the subsequent chapters. Okay, so the important part here is we have some equation for calculating our mean. Okay. So if we calculate our mean, it's given by the summation from I equals 1 to n of x of I, and all divided by n. Okay, so let's start with notation, just to go back if you guys don't remember it. Summation, we're going to start from I equals 1 and add up I1, I2, I3, I4, I4, I5, all the way to In. Okay? And then we're going to divide everything by n. So, and if you ever see me do the ... understand that's just follow continuation of the pattern. Okay. Why is this important? All right, let's do change the layout. I thought that was in here. There we go. Okay. Let's talk about let's say I take all my measurements, let's say we're measuring how long this table is with the ruler, right? So I have all you guys come out and measure it. And you come out with some samples, y1, or x1, x2, x3, ... to xn. Okay. And these are in units of inches. Okay. And I say, well, you can calculate the average, ask you guys, calculate the average length of table. Oops. Okay, so you guys would just apply the equation, and you would be able to calculate x bar. Okay, what units are x bar going to be in? Okay, so not particularly challenging, but why is this important? This is important because my next question is, what if I want, and I know this sounds silly, but just work with me here because it's more of the thought process. What if I want the sample average in meters? How would you guys calculate the sample average in meters? I say this table is 40 inches on average. That's the sample average. Bring it in the back. Okay, yeah, you can do that. So you could convert all our samples from inches to meters and then take the average of that, right?
Because it's like a set measurement, a set conversion, just the final what you have that.
Yeah, so the alternative is we take our sampled average, which is in inches, and we apply the conversion over. So we can actually do that, okay? And what we're doing is essentially applying the linear transformation on our data. So I don't know what is it? Inches to centimeters. Oh, 2.54. Okay, there we go. 1 inch, 2.54 centimeters. Okay. And I'm just going to call this M. Okay, just to make life a little bit easier, I'm going to call this value M. So if we wanted to calculate our sample average centimeters, what we could do is we could say, well, x bar in centimeters is equal to 1 over n, the summation of I equals 1 to n, and we could multiply each xi that we measured times this 2.54. Okay, and that was your suggestion, right? Yes, sir.
Well, I was going to ask, if you talk about doing a linear transformation.
Yeah.
So 2.4 centimeters isn't exactly an inch. Is it better or worse or exactly the same to multiply the data by that or multiply that?
That's what we're going to figure out. Yeah. So it ends up being the same. That's the end message that we're going to try to get to is that if you ever have a system where you have some data x and you're going to say, well, we're going to transform that into y, where y equals mx plus b. So this is a linear transformation. Right. Then what I'm going to tell you is y bar, that average, is just equal to m times x bar plus b. Okay, so that's where we want to get to. And so we can sort of see that here in our simple transformation. All right, so actually, why don't we... So here, instead of y, I'm calling it x centimeter. And I'm saying the average in centimeters is just equal to the average of all the x of I times 2.54, which we take as the conversion, right, as truth. Okay. And so what we can do is, just using algebra, we know that this is a constant inside the summation, so we can actually just pull it out. So what we see is, we say that that's equal to 1 over n times 2.54. My dead pixel, sorry. X of I. Okay. So all I did is pull out that 2.54. Now, of course, we can reorganize this a little bit more and just put the 1 over n in front, or closer to the summation. All right. And now we're left with that original equation that we would have used to calculate our sample mean. And so we can just substitute in what our sample mean is. And where's my screen die? Okay. So sorry, my screen dies right around here. Okay. So I'm still learning this. And so what happens is this x centimeters is just equal to 2.54 times our normal x bar. That's not too bad. That's not too bad. All right, so if anybody wants any extra credit, go ahead and generalize it. All right, if we have a plus b in our equation. Yeah.
So the a plus b, it would be something times, so we divide by the n.
Show me the steps. Turn it in. You'll get your extra credit. Not today. Bring it to me tomorrow. Okay? So, extra credit if you guys want to do that. All right. All right. Why is this important? So it's sort of a shortcut in life, but you're going to have to be careful about applying the rule, all right, or this idea. Okay. And the reason why I want you to be careful is, let's say you said y is equal to x squared. Okay, or actually we can make it more complicated. Yeah, let's do that. My question is y bar equal to 1 minus x bar squared taken to the square root? Actually, we'll add this to that extra credit, right? So if we'll do this extra credit. And we'll make it a little bit easier. Why don't we do this? Okay. You tell me if this is true or not. Okay. Anybody want to guess what the answer to that is? Okay. Well, yeah. Yeah, I don't think it's true either. Excuse me? Oh, so you can. I don't know. So what you're going to want to do is apply your mean equation here, right? So the general idea is we know y bar is equal to, it's still 1 over n, the sum of I equals 1 to n y of I. Okay, and you just plug in y of I into there. Okay. And tell me what you get out. Actually, that might be too hard for you all, but go for it. But the end answer is they're not the same, but I want you to show that, okay? Linear transformations are very special because they preserve a lot of interesting properties, right? And preserving the sample mean is one of them. Okay. There's another property that sort of gets brought up on page, what is it? Somewhere on here. Yeah. On page 40. So if you go to your book, if you guys have it. If not, you can see it in the notes. They basically put forth this idea with the standard deviation as well. Okay? And they start with, well, let's say your y of I is equal to x of I plus c. And we can calculate what the sample mean of x is, or the standard deviation of x. Okay, we can calculate that. So the question becomes, what is the standard deviation of y? And if you work through the equations, So actually, let's maybe think about what's happening here. So if I have every x value, okay, so I'm gonna we got a dot here, a dot here, a dot there. Okay. So these are a bunch of sample data points, the red dots. Okay. And I add C to each one of them. What's going to happen to these red dots on my number line? They're just going to shift all together. Okay? So we can sort of draw that pictorially. So if they all shift together, did they spread out any more or less? No, they didn't. They stayed, they maintained their variance, okay? And so what we should expect then is that the variance that we started with, or the standard deviation that we started with of our data, is preserved, okay? So the standard deviation of the y is preserved if we just add a number to it. Now, that's not true when we multiply each of our data points. Oh, I have to be careful how I say this. Okay, so let's sort of take a look at this case. All right, and I'll do it on another slide. Okay. So, and I'm going to center it about 0 so that you can see it a little bit more. All right. So we have a bunch of data points. I'll even put one at 0. And now we're going to multiply all our data times 2. So I'm just here making up an arbitrary number. So y of I equals 2 times x of I. Okay, so our data points are going to become twice as large in each direction. Okay. So if we draw that, you know, this guy at 0, still at 0. This one, he gets 2 times further out. Same thing with this guy and that guy. So all of them get spread out a bit more. Okay. So now the question is, what happened to our standard deviation? Is our data further out or closer in or the same? Further out, it's more spread out. Yes, sir. Yeah. So it spreads out. Right. And so what happens is, if we want to know what the standard deviation of x is, or y, sorry, after we apply this transformation, it's given by the absolute value of whatever constant we're multiplying by times our original x data, or the standard deviation of our original x data. So in this case, our standard deviation goes up by a factor of 2. So if our standard deviation was 2.3, it now becomes 4.6. Right? Another question to think about. And, you know, this is more of a thought process. Let's say our y of I, is equal to the negative of x of I. According to the last equation I just wrote down, okay, the standard deviation is the absolute value of c times s of x. So in this case, what's our c value? 1 or negative 1, right? All right. So we end up with s of x, absolute value -1, s of x, and absolute value of -1 is 1. Okay, so does the standard deviation change? No, okay. And intuitively, this kind of makes sense, right? Because we haven't actually like spread the data out, we've only flipped it onto the other side. Okay, the data is still distributed in the same way. That is like, yeah, okay. Okay, so before maybe all our data was over here, and we might have had one negative point, and now it just sort of flips. Okay, and the standard deviation stays the same. It's just our data shifted, but the spread is the same. Okay. How many of you guys are mechanical or electrical engineers? Oh, wow, good bit. Okay. So do you guys have to take linear systems, control systems, right? Maybe. I think you will. I'm pretty sure most MEs have to take it. I think ECEs, you might have like linear system theory or something like that. Okay, this is going to come up in your linear systems class. Okay. Because what happens is you're going to model a lot of physical phenomenon, okay, using linear equations, okay? And the question is, how does standard deviation or errors get magnified or shrunk down? Okay, so let's think about it this way. Let's say I have an audio signal and I stick it into an amplifier. Okay, what does an amplifier do? It makes everything louder by some gain. Okay. If I do that, I should expect any noise I have in my original signal to get even noisier. Okay, does that make sense? And so you'll see stuff like that. All right, so this is more, I guess, a mathematical. I want you guys to sort of understand some of the mathematics behind it, beyond just, okay, can we do our problems? All right. So for me, I think those are some of the bigger things. What I want you to be able to do, and actually I might make this an assignment, is to be able to prove this fact. Okay. Let me be specific. Prove this fact, starting from the equation of the standard deviation. Okay. So what I'll do is, again, extra credit for the mean. It's due tomorrow. I'll post a video on the solution, and I want you guys to take a look at it, understand it, and then we'll have a little in-class quiz on the standard deviation. Okay? So take your time this weekend, derive it, and show that this is in fact true. Okay? And then Tuesday we'll have a little quiz on it. All right, so you know what the quiz question is. All right? Prove. Okay. And look at how I prove it for the mean. Okay? So you guys can structure your argument the same way. All right, so let's maybe get to the flipped part of this class. So what did I say a flipped class was? You guys watch the video. But what happens in class? So normally I teach you in class and you guys go do your homework at home. The flip of that is what? Right, and we will literally, and we are literally today going to be doing the homework in class, okay? So, what I want, look, well, we'll see how this, all right, so what we're gonna do for the remainder of the class, we got about 40 minutes. We're gonna start going through the homework, okay? So what I want you all to do is, can you guys get into groups of 3 and make sure there's one new person in your group from the last time, okay? right.
Sorry, excuse me, I need to take a phone call.
Go ahead. Yeah. All right. So what I'm going to do, I'm going to pull up WebAssign on the screen. If you guys have your laptop, pull it up as well. Okay. I'm going to pull up Excel. All right, and we're going to start working through these problems. And they're not so hard, right? But the key thing here is WebAssign gives you different numbers for everyone, but the procedure is the same. Okay, so if you can solve it, whatever's on the board, essentially you do the same thing on your homework, you'll get the right answer. All right. So I'll bring up my version, and we'll start working through it. All right. Okay, so what I want to do is I trust you guys can all make stem and leaf graphs, yeah? Okay, so I don't really care about that. But what I do want to do is tell you that I think we decided we're going to use Excel and not Python, right? Yes. Yeah, okay. I know we have uneven Excel levels here. So what I'm going to do is basically go through some Excel really quickly, and we're just going to solve these problems, okay? In our exams, you're going to be expected to know Excel and be able to do it very quickly, okay? So you'll basically end up having exams that are like these homework assignments, okay? So doing them by hand is going to take you too long. I do not expect you or want you to calculate the standard deviation manually, okay? Excel has functions to do that. Right? The only time I expect you to work with those standard deviation functions or mean functions or anything weird is on these sort of weird mathy stuff that we discuss every now and again. Okay? All right. So with that, let's see. So we're going to answer some of these questions. I'm going to work through this first one only because I want to share with you some stuff that I learned. I don't know Excel very well, but we'll figure it out. Okay, so I'm just going to go ahead and copy these values over to Excel. And I think I already have some solutions. Oops, enable editing. Okay, so I just did Control-C, and when I paste it, I do a paste special text, and that actually formats it. Otherwise, if you just do Control Copy Paste, you get it on 2 rows, which isn't particularly helpful in this particular case. Okay, so we have all our data right there. Okay, so the problem that they're asking here is to do a stem and leaf diagram Yeah.
I'm sorry, can you repeat?
Oh, sorry. Yeah, I just right-clicked, and the drop-down menu comes down, and I said paste special, and select text. Okay. All right. So, and this, I'll try to put this on YouTube again. So if you guys want to follow along, you can do that. So let me start with, you should have no expectation that these videos are ever on YouTube. Okay, so don't think, oh, Professor Vela records them, they'll be on YouTube. This fails all the time, and it will fail more and more as the semester goes because I run out of space on the SD card, and SD cards start crapping out as you start hitting their memory limits. Okay, and sometimes I'm just busy, and it'll take me 2 weeks to post. All right, so we got all our data posted. Stem and leaf diagrams, I think we discussed them last week. What do I think about stem and leaf diagrams? Say again?
Good way to teach.
Yeah, good way to teach, but not particularly useful. We might as well just use a histogram or a bar chart, okay? So Excel certainly has a histogram function. You can highlight your data, go over to insert. I think this is the histogram. Yep, statistic chart, and then histogram. All right, anybody see a problem with this? Yeah, I don't like my bins very much. Okay, so sure, you can, I think, click on the bin. So I just double click down there. And I can say, well, I want to change the bin width. What if I want to make it 1? Okay. What's the other issue? What issue am I left with now? So can somebody read my bin edges off? Yep. All right. So if we look at our problem, right? They wanted, easy bin edges, right? I mean, this is for the stem and leaf, but we're just going to pretend it's a histogram. They want 5, 6, 7, 8, 9 times. Okay. For some reason, the histogram function doesn't let you clearly define your bin edges. Okay, where to start and where to end. All right. So this histogram graph is more or less useless in Excel. All right. So that said, does anybody know the alternative? How to make one? No? Okay, I had to learn. So let's see if I can even find it again. Oh. Man, do I even have it? Okay. Oh gosh, what's the word? I was just doing this. All right, I'm going to pause this because I suspect there are going to be like 5 different ways to do this. Okay, so this will just be one of the ways that we can do this. Okay, so don't take this as the only way. As long as you get your answer for WebAssign, that's all that matters, right? Okay. So there's something called frequency, and the way that we set it up is first you set up your bin edges, all right? And so for the problem, they wanted the bin edges, like at, let's see, 5, 6, 7, 8, 9, 10, 11. Okay, so here we're going from 5 to 6, 6 to 7, 7 to 8, 8 to 9, and so forth. Okay. So what you can do in Excel is you go ahead and set up your bin edges as a list. And I'm just going to make mine a little bit larger than the 11, and you'll see why. All right. And this next column, we're going to stick in the counts. Okay. This is where things get a little bit weird. So we're going to use an equation called frequency. And I always do this wrong, so you'll have to be patient. What you're going to want to do is you're going to want to highlight or mark the values that you're going to put into the histogram. Okay? And so here we're doing A1 to A27. All right? And then what you want to do is actually feed it in the bins, the bin edges. All right? So we're going to mark in this guy. All right, and you can see now it says C2 to C9 right there. Okay. I will get this wrong for the Mac people, but okay. So right now it says there's 0, and we'll sort of see why. Because what happens is it's actually counting from negative infinity until 5 how many values are in that bin. Okay, and we can see our first value starts at 5.8. Okay. So here's what you do next. All right, so let me refresh. You click on that first 0. You click here on frequency. All right. So you see how I put my cursor up on frequency, and at that point, oops. No, what did I do wrong? Sorry, you drag down. Click on frequency. There we go. Oh, I'm sure I did that wrong. Okay, or not wrong. Didn't explain it right. All right. Drag it down. Click on frequency. And then for me on a Windows machine, I press Shift, Control, Enter. And it will do the counts. Okay, on a Macintosh, I think it's your funny command thing, right? I don't know what. Yeah, Shift Command Enter. So did you end up getting the same values?
Yeah.
Yeah. Okay. Shift Command Enter. All right. So now this starts to make a little bit more sense. Okay. We have one value between 5 and 6. I'll show that over here. So we have one value between 5 and 6, that goes here. We have 7 values between 6 and 7. All right. Where else? Is there any more? 1, 2, 3, 4, 5. Might be missing one. Yeah. Did that work out right? Yeah. Yeah. So it's a little bit confusing. It took me a while to figure out. All right, so, oops. Yeah, so we can always do that. Well, yeah. So I'll go ahead and actually sort the data first. Data. Okay. Ooh, how did it get 7? Oh, okay. 1, 2. Ooh, something seems not right. 1, 2, 3, 4, 5. This is very suspect. Very suspect. Okay, so what should be happening is, in the first cell, you type in frequency. Oh, come on. Although now I'm not trusting this thing. All right, you give it your data, and then you press comma, and you give it the edges. You press enter. Oh, what didn't it like? Oh, I'm gonna have to, I think it's, okay. Frequency. Data. Edges. Okay, press enter. Okay, so in theory, if you click on the word frequency, it highlights the column on the left. And somehow what we want to do is apply that equation down the column. All right. Oops. That's not what we want. Although I don't trust this very much now. Yeah. There we go. All right. So the key here is you're clicking on frequency and pressing Shift Control Enter on the highlighted column. So I highlighted it, and then it should redo the calculation, but I don't know if I like that. Something seems wrong, right?
Can you look at maybe one of the lower cells just to see what the equation actually says?
3. Is that right? 3, 1. Why do I not trust the 6 to 7? Oh! Does anybody see what I see here? How many values are between 6 and 7? 7. So it's counting the 7 as in the bin. Okay, so the key lesson here is that when you do these bar charts, okay, it defines the number of elements in the bin as the number that, so it's doing this, right? It's checking how many values are greater than 6, but less than or equal to 7. So that's why it's counting the 7s here. Okay. Yeah?
So you have 0 or 5?
Because that's the upper bound.
Okay.
Yeah, so actually, for here, it's saying how many values are between negative infinity and 5. Okay. Yes.
So if you wanted this to be different, would it be okay for submitted assignment to put, depending on how the data is set up, of course, like 6.99?
Yeah, so let's do that, because we want to actually get something that looks similar to what WebAssign does. I'm surprised that Excel does it that way. Normally, most people do this. Okay. This is what I'm used to, where the upper edge is strictly less than. But, okay. Peculiarities of Excel, right? Okay, but the important part is we can adjust this, thank goodness. So if we want to sort of get rid of that, what, feature, maybe? Let's do this. Oh, I can't change any of the array. So, I can minus 0.001 from everything, yeah? Although it's not a very pretty solution, I can do it. Yeah?
The question is showing up for 9 specifically as a bin edge. It's showing up as 4, but there are only 2 or
Ooh, that's...
6.
No, wait, hold on. 1, 2, 3, 4.
Oh, is that for 9? No, not for 8. Oh,
It's
right.
8 to 9. Yeah, so it shifted off
Sorry,
1.
yeah.
Okay, yeah, that's good. Yeah, so be ever cognizant of. I hate the way this doesn't do tab completion. Okay, so if we wanted to, we could use these adjusted bin edges. And again, you sort of highlight what you want. It's going to spit out erroneous data. All right, you click on the word frequency, and in my case, on Windows, Shift Control Enter, and it should correct it, hopefully. So does this look better or worse? All right, so now, how many values do I have in the 6s? I have 5, right? Which is what I want. Okay, cool. All right, so from there, it's pretty easy. Well, not easy, but you can make a bar chart, right? So insert, let's see. But I'm going to use these bin edges. And we can go ahead and make a bar chart. Okay. So, all right, so that probably took way longer than it should have. Okay, let's get through some real problems. Okay, actually, let's answer these first. All right, do these observations appear to be highly concentrated? Yes or no? No? I kind of lean towards yes, but I could see how you might say it's not because of this value, right? You said yeah? Okay, so the answer is no. Okay, all right, so which way is this thing skewed? Positively. Okay, so remember when we're talking about skew, we want to know where the tail is. Is the tail more positive or more negative? So here we have a longer tail on the right, so it's positively skewed. Cool. All right, what else does it ask? Do there appear to be any outlying strength values? So I disagree with some of these questions, but outliers, look, let me tell you something that I see students do far too often, which is overrepresent what is an outlier. Okay? Does anybody know our basketball team? Anybody know the 7'7" guy, our Florida native, right? He is huge. Okay, is he an outlier? So who could make an argument that he is an outlier? Well, that's certainly true. So he's certainly not within the 99th percentile. Right? Actually, we probably should not make this very personal, right? I don't mean to do that. But like, what makes him an outlier? Okay? He is human just like the rest of us, right? He went through the same natural process as the rest of us. What makes, sorry, and I don't want to use George Murasan an outlier or not, okay? So understand that many times in statistics, when we put the word outlier on something, I tend to think of it as the process by which that data was generated is the outlier. Okay? So what do I mean by that? Let's say I have a set of calipers, okay? And I keep measuring the size of the table. And then my calipers break, and I try to measure the table, okay? It's going to give me an erroneous answer because the measurement tool or process is broken. It's no longer the same. All right? So for me, that is representative of an outlier, which is the underlying process that generated the data is different. Okay? So when you look at data, I think you should think about it that way as well. Okay? So just because you have long tails does not mean the data at the tails is an outlier. So does that make some sense to people? Okay. So another example of this is, I don't know if any of you scored perfect scores on your SATs, but you could be considered an outlier. Okay? But thousands of students every year score perfect on their SAT math or SAT English. Okay? It might be a statistical outlier, but it doesn't make those people any different from anybody else, except, yeah, they're good at math and they got a good score. Okay, okay, more philosophical. Let's get through the rest of these real fast. Okay, so I think you guys can handle most of these. All right, so I'm skipping down to problem 5. All right, what does it ask us? Calculate the sample mean for each of these two groups. Okay, for urban and farm homes, we have data about what? Concentrations on dust. Okay? Not too hard to do this. All right, so we go ahead, we copy our data over to Excel. Oops, and I'm going to do a paste special. I know some of you can't quite do that for some reason. So this is, I don't know, the 5th problem. Okay, so I'm going to look ahead and see what the questions are asking. So it's asking us for the means. Later it's going to ask us for the medians. Anything else? Oh, trimmed means and trimmed percentages. Okay, so actually go through this really quickly if you guys sort of want to follow ahead. Anybody know the mean function in Excel? Average, yes. So we type in average, we highlight our data, we're all set. All right, so I got 21.54. I don't know what you guys get. We can drag that over and get the mean for the other data. You guys can go ahead and type that in. That's your answer. We can calculate the median in a very similar way. We just use, what's the function for median in Excel? Median, yeah, okay. All right, highlight our data and drag it over. Okay. Ooh, actually I made a mistake. B11. Okay, so a couple of things to learn that are worth learning. So here I can actually take the mean from the first item down to the 15th item if I wanted. All right, and it just treats anything that's blank as no data. Okay, so you're fine there. But if you have zeros there, of course, that will change your results. Okay, so we can calculate our medians. Okay, another useful function you'll want to use. And actually, we can go through and what does it ask? How do they compare? Okay, so let's start with first one. Okay, how do the averages compare between the urban and the farm? Yes, sir. The urban is higher. Is that what we got? Yes. All right. 21.55 if we round it, and 8.53. All right. Okay, cool. So we can answer that question. We can do the medians. So how do the medians compare? So which one's, I think the first one was urban, 17. Rural, how do the medians compare? Urban's higher. Okay, so not too challenging. We got that. Okay. Oops. So that one. Okay. All right. All right. So trimmed means. Okay. So what we sometimes do is folks will say, I want to exclude the top 10% and bottom 10% of my data to calculate the mean. All right. If you read the book, you'll understand. Actually, why do we do that? For those of you that read the book. Well, yeah, why do we trim the mean?
Sensitive to the outline data points, so when you trim the mean,
Yeah. Well, let's be careful. But yeah.
Like more representative of what.
Yeah, so it places greater importance on the central data as opposed to the outliers, and I think that's exactly right what you said. Okay, so sometimes we want to trim the mean, and Excel has a nice little function to do that, and it's called trim mean. All right, and again, it's more or less the same. You highlight the data you want, and the tricky part that I found is it accepts the percent, but you actually give it in decimal form. So if you want to trim 10%, you do not stick in the number 10. You stick in the number 0.1. Or do you? Ooh, is that right? I'm almost certain this is the one that weirded out. Yeah, so it barfs. Okay. So you put in 0.1. Okay. And so this will trim both ends. Right. We can take this over and do the same thing. Ooh, these trimmed means did not change very much, did they? Oh, wait, how much did they want to trim off? Oh, they said smallest and largest. Okay, so actually, and they also did percentages. Okay, all right, so if we want to trim the smallest and largest, we have a couple ways to do that. We first have to find the smallest and largest. So what's the best way to find smallest and largest? Sort it, yeah. So why don't we go ahead, just sort our data. There's another tricky way you can do it, but I'll put a video on that. Okay. All right, so we sort our data, and now we just do the average. And they said drop the first and last, yeah? All right, so we just go from the second to the second to last. That's not too hard. And amazingly, it's actually the same as the median. It's a little bit surprising. Okay. All right, there we go. Okay, cool. So we got trimmed means. All right, so you guys now know that function. Okay. What else did I want to do? Okay. I think we're gonna skip. Okay, so you guys know how to calculate the mean, the median, the trimmed mean. What else did we learn in this chapter? Standard deviation. Okay. It's pretty straightforward, so I'm going to work with problem 10. Oh, and this actually has a few weird questions, right? Okay. All right. Okay, so again, I don't expect you guys to go through the manual process. Just go ahead and use Excel. Put them in there. In Excel, it's standard, what, dev, I think? STDev, yeah. Okay. Oops. And you highlight the data that you want. Okay. That's not particularly hard. So that's the standard deviation. So that's actually not what the first question asked. So what the first question asked? The range. All right, can somebody tell me what the range is equal to? How do we calculate it? Highest minus lowest. Okay. So all we have to do is subtract the min and the max from each other. So we can go ahead and just say max, highlight our data. Oops. Oh, go. There we go. Minus min. Bam. We got our range. 2.1 for me. You guys have different values, right? Yeah, okay. All right. So next it asks for variance. So we actually went out of order. Let me mark these down. Okay. So variance is just var and our data set. So that's not too bad. All right. And if I want the shortcut of getting standard deviation, all I have to do is take the square root of my variance. Is that right? Hopefully they give me the same thing. Yep, there you go. And I think that's what they mean by the shortcut, right? Is that in this question? Yeah, using the shortcut method, sure. Who knows? Actually, I don't know what that shortcut method is. Okay, doesn't matter. You get the same thing. Math doesn't change. Okay. All right. So I got that pretty straightforward. There was one other problem. Oh. Okay, so hopefully we can do this in 5 minutes. So I want to do this last problem 12. Okay. So I'm going to go ahead and copy all this data to Excel. And here I think I'll just paste it. Oh, no. I don't want to match format. Okay. All right. So the first question, and the reason why I'm doing this is because it's going to ask us to generate some box plots. And so I just want to show you guys how to do that if you haven't done it before. All right. So first questions is to just calculate the medians. All right. Again, that's more or less straightforward at this point. We just type in equals median, and you highlight all your data. Press enter, right, and we can drag this equation over. Okay, so you go ahead and type it in. All right, so not too hard. Next, we'll just calculate the standard deviation. We've done that again before. ST diff. All right, so let's maybe answer some of these questions. Okay, so we got our medians and we got our standard deviation. All right, and it asks us to compare the standard deviations. And basically it's asking, does it increase, decrease, or what based on the type of chamber that we're using, if it's a cooler, controller, or warmer. Okay. And so if we look at the standard deviation, do we see any sort of pattern in row 19? So 0.39, 0.52, 0.78. These numbers are getting bigger. Yeah, it's increasing. Okay. So we'll find the appropriate answer. Yeah. Which is, as we go from the cooler to the controller to the warmer, the variability increases. All right, so I think that's the right answer there. Okay. So then we talk about, I have 5 more minutes, right? 2? Okay, well. Force spreads. All right, so I want to show you guys this very quickly. Do you guys know how to calculate quantiles in Excel? Oh, okay. All right, so we're going to rock and roll through this. It's not too hard. All right, let me... Yeah. All righty. So I already have the data copied down here, at least for me. So the equation you want to use is just quartile. Okay, so that's what you see here. Okay. You then give it your data set. So here I went A1 through A15. And then you tell it what quartile you want. So the first quartile gives you the 25th percentile. The second one gives you the median, so you're at 50th percentile. Third is the 75th. And then finally, the fourth should be the 100th, right? Oops. Okay. All right. So here, when we talk about calculating the force spreads, what we're taking is we're taking the 75th percentile, which corresponds to the third quartile value, and we're subtracting the first quartile value from it. Right. So if we go over to our Excel spreadsheet, all right, we calculated this first quartile. So again, you can see I highlighted my data, and I said calculate the first quartile, number 1. I calculate the second, and here goes the third. Okay, so again, I take my data, I say calculate the quartile, and I want the third one. Right. So if I want that range value, the fourth range, is that what they called it? Fourth spreads, I just subtract the third and fourth, okay? So I'm subtracting this calculation and this calculation from each other to get 0.39. So, not too hard. Do you guys want me to go over how to do box plots in about 30 seconds, or do you want to get out of here? Okay, I will show you very, very quickly. Okay, look, highlight your data, insert, and there should be a box plot somewhere. Where'd it go? No. I'll put it in a video, okay? All right, get out of here. Okay, so this is what we're going to do from now on. Again, you guys need to read the book beforehand. What's the quiz on Tuesday? Yeah, and I will put in how I would do it for calculating the mean. You guys follow the same process. You guys are, of course, encouraged to study together and solve this problem together before the quiz. But when you do the quiz, it's on your own.
What do we have a quiz about?
Ask your lab mates. I think that would be the best thing.
What do we have a quiz about?